first people to invent a wind tunnel were actually the Wright brothers. They hypothesized that so they started experimenting with kites, and they figured out that if here they are holding their kites. Okay, so they made this discovery, or they hypothesized that if they created a kite that flew at a higher angle, that means its lift would be greater than its drag. So drag is what causes the kite to blow downwind, and lift is what makes it go up. So the air flows this way, and so they discovered that the best shape was with the apex of curvature, the deepest part of the curvature, approximately a third back from the leading edge. Actually, it was between 30% and 40%. So if this is 100%, then this would be 30 to 40%. So this shape created the, it allowed the kite to fly higher. And so this is very important in sailing because this little difference in the angle here, it makes a big difference on a sailboat. Okay, now I want to do an illustration to show the difference between drag and lift. So let's say we want to have something fall out of the sky towards the earth as slow as possible. So the first thing most people think about is a parachute. So a parachute is basically a semicircular shape. Here's a little person here. Okay, so tests have determined that a hollow semicircle with this orientation will create the most drag, basically. So it's basically like a big scoop, and what happens is it just captures all this air on the bottom side, and it has no way to escape. It just hits itself, and then it goes this way, and then it's hitting this air. So what does it do? It basically captures a bunch of air, and then the air on the backside, it runs into each other this way, and it can't generate any velocity, and so it just creates rolling vortices that shift from so the vortices goes like this, and then it shifts on this side, so it goes from this left to right, and it just moves around. Now the reason that you have to hang and put a lot of weight, the only way a parachute keeps its shape is if it's there's a lot of weight, and the weight is well below the center of the parachute. So you have to have a certain distance for this shape to remain full of air. Let's say we took the person off and we made this like a shell, like a solid hard plastic shell or something like that. The first thing that would happen was this thing would flip upside down, and it would basically fall to the sky in this orientation, kind of wobbling a little bit. But so what that means is this orientation is very unstable, and it doesn't want to stay in this orientation. It wants to flip over immediately. but because of the weight and all these ropes, and actually the velocity. So as soon as the paratrooper hits the ground, you'll notice like the parachute shape will like collapse. It'll just fall apart. As soon as the velocity goes away, the shape goes away. All right, but there's another way to fall from the sky. So the velocity, the average velocity of a parachutist is about 17 miles per hour or 17 knots, in that range. Okay, so I'm going to draw something else. It's an alternative. All right, so so this is a glider. It's also called a sailplane, and it also falls to the ground, but it falls a lot slower. And so let's look at the glide slope. For every foot or a meter that the sailplane goes down, it goes as much as 30 sideways. So the glide slope is 1 down and 30 sideways. So, and they travel at around 90 knots or about 85 knots. So that means if you calculate, they fall down from the sky at exactly 2 to 3 knots. So compared to 17. So which of these is better? You would think that, oh, this is better, but actually it's not. So the difference between these two is this is deep curvature, semicircular. It doesn't really have a leading edge. So the leading edge and trailing edge are basically the same, and they compete with each other. This has a leading edge, and the air is the length is so the longer you make the aspect ratio of the wings, the greater the lift is. So lift is proportionate to aspect ratio. And so because the air is mostly flowing from the front, you create this streamline hull shape. And okay, the other thing is you can't have a sailplane without a tail. That's the other thing about lift that a lot of people don't know. So there's two things that happen when you when you have a curved shape. The one thing that most people know is, oh, there's a lift generated. But the second thing is there's a rotation. So the wing, if left by itself, would want to rotate in the direction of the curvature. So that's why you have to have a tail. The tail actually, so the lift is generated by the main wing, and the tail actually creates downward lift. And the downward lift of the tail is the reason, okay, so the center of mass, or the pivot point of the sailplane, is along the wing. And so that's why this can be much smaller, because it's farther from the pivot point. So the tail does not have to be anywhere near as long as the wing, because this is at the pivot point of the airplane, and this is way behind it. So that's why the tails are much smaller than the wings. So there are a couple steps in between most drag and most lift. So you can go, you can actually have a parachute that's elliptical shaped like this. It's still, there are some parachutes that are, instead of round, they're more elliptical. So, or they're kind of square on the ends like this. And this kind of parachute is not as deep, and it has a leading edge. So you can actually steer. So this paratrooper can actually, he can steer. But he still has to be hanging below the parachute for stability purposes. But he can pull on these two ropes. He's got a rope that kind of pulls here and a rope that pulls here. And the airflow is mostly in this direction. And unlike this, where this does not have a leading edge. So on a sailboat, a spinnaker is very much like this parachute. It's designed for going straight downwind, and it's very unstable. And if the wind dies, it'll collapse. And then this parachute is similar to an asymmetric kite or spinnaker, which does have a leading edge, and it's a little bit more stable. And this parachuter will probably fall to the earth slower than this guy. And it has to do with the velocity, because this guy is now traveling at, let's say, maybe a 45-degree angle down, or I don't know what that angle is. I'm just making that up. He has more velocity sideways, so the flow of the air over this curve is going to be higher, and therefore it's going to generate a little bit more lift. Okay, so then there's another step between this, and it's called a hang glider. Let me see here. Hang glider kind of looks like this. So a hang glider is like this, and it's got like a triangular thing where the guy hangs underneath it. Now, the hang glider does not have a tail, but it does have wings, and it does have spars that keep this aerodynamic streamlined shape. However, because it doesn't have a tail, it still is a little bit unstable, and it has a tendency to pitch downward. So that's why when you're, that's why the weight has to be hanging below the wing. The weight hanging below the wing is what gives it its stability, and that's what keeps the nose from pitching downward. So on a sailplane you need a tail, but on a hang glider you don't, because the weight being positioned below the hang glider's wing is a counterforce. So if this is the wing, and here's the weight, so you still have the weight down here and the wing up there, and that's what keeps the nose from diving. Because as soon as it goes down, the weight will correct it. Okay, so those are like 4 steps between this, which is total drag, and there's no leading edge, no trailing edge, to yes, it has a leading and trailing edge, and in each of these steps, the wing gets longer. So, and the speed, the horizontal speed, gets higher, and the angle of the triangle gets more like this. So so drag is basically going against the flow, and lift is going askew to the flow, or almost 90 degrees to the flow, but not quite. So let's say 3 to 8 degrees or so